Well, dear students, in our last session, we have completed the chapter 1 according to our curriculum. The chapter was electric charges and electric fields, in which we have learned the various properties of electric charges, which are at rest. Right? Like what is electric force between charges according to Coulomb's law. And we also learned what is the field intensity due to a charge. And we also learned the lines, electric lines of force being drawn in electric field. The lines are due to charges, and number of lines, as you know, directly proportional to the magnitude of charge. Followed with, we also learned the flux of electric charge. Flux due to electric charge in an electric field, which is a measure of the number of electric lines. And followed with, we also learned the application, the Gauss's theorem, the application of Gauss's theorem, where Coulomb's law has limitation, where we can find out field due to distribution of charges using Gauss's theorem. These are the important highlights where we have discussed in the chapter 1. And in chapter 2, we are continuing the discussion of what is called electric charge properties. We will continue to discuss the other properties of electric charges, in which essentially the one property called electric potential and followed with the what is called capacitance we learn in the chapter 2. So what is electric potential? Like you have an idea of what is called gravitational potential. Like gravitational potential. Gravitational potential we have defined earlier in the first year course. Similarly, electric potential, gravitational potential refer to gravitational force, and that is due to mass. Electric potential due to electric charges is another fundamental property of matter. Electric potential on account of electric force, and to be measured in an electric field. Gravitational potential we measured in a gravitational field, and we know that it is the work done per unit mass of a body is gravitational potential. So potential energy by mass, potential energy by mass is the formula for gravitational potential. Now we come across the term electric potential. Electric potential. This is symbolically V. Even this one also symbolized with V. And it has formula written earlier minus Gm by R. R is now electric potential. Potential is like a level, and it is defined. To understand the definition, of electric potential, let us consider a charge Q, positive charge, placed in a space, free space, that is air or vacuum, and we can find out what is the electric potential of this charge at any point surrounding it. Say, let us find out the electric potential at this point. At this point B. Say distance r from this, you can find. Similarly, we found that gravitational potential due to Earth at a distance r from the center of the Earth. Similarly, now we are considering a point charge plus q in space. Let us find out its potential at point B, distance r from it. In order to do so, according to the definition, the potential similar to that of gravitational potential, electric potential, it is the work done. What for? To move a unit positive charge from infinity to given point. This is the given point, and now we have to bring a unit positive charge from infinity to this point. And you know very well, this charge has electric field, and if it is positive charge, electric field will be away from it. This is electric field direction. This is moved up to where? Up to here. But while moving, it should face the opposition due to electric field of discharge. It should face opposition due to electric field of discharge. Opposition. So, in spite of opposition, if you are able to move the charge, then you are putting effort. So, you are spending energy. That energy will be accounted. And how much that energy you have spent per unit positive charge is referred as electric potential. Electric potential. So, I write it is the work done. It is the work done in moving a unit positive charge. Unit positive charge from infinity to the given point in an electric field and against it. In an electric field and against it. This is the definition. So it is electric potential is the work done in moving a unit positive charge from infinity to the given point in an electric field and against it. So that I write the definition P. From infinity to P is equal to work done to move from infinity to P. This is the work done. This work done per unit charge. This marks the definition of electric potential. This is the definition of electric potential. And the Q value is being +1 coulomb. Therefore, if it is +1 coulomb, unit positive charge, then work done is equal to potential. Work done is equal to potential. So, potential is in term means the work done. Work done. Work done. Whenever you use the word work done, there should be a purpose. Why you do work? So work is done. Say for example, to lift a mass against gravitational force. Work done to elongate the spring against the spring force. Similarly, work done to move a charge against electric field. Work done maybe by the force or against the force. A particle falling freely, work done. The gravitational force, a particle thrown up, work done against the gravitational force, like that. So this work done is numerically equal to what is called electric potential. Yes. Therefore, potential, now we write the SI unit, it will be work done by charge. Ambre, this is joule per coulomb. Work done, SI unit is joule per coulomb, remember. Now we are going to also find the formula for potential due to a charge at this point. So it depends on distance. As the distance increases, potential of this charge decreases. As the distance decreases, potential due to this charge increases. Potential in other way is also referred as what is called strength of a charge at that point. Potential is also in turn referred as level. In fact, remember, I have mentioned very clearly in the earlier class the terms like potential is equivalent to what is called a level, is equivalent to what is called a temperature. These are analog terms. Potential either with respect to electric potential or gravitational potential. Level of water in a vessel. Remember, level of water in a vessel, level of liquid in a vessel. Temperature of a body. These are correlated terms under different contexts. However, they give similar kind of meaning in the respective parameters. Remember, potential is like a level when you consider liquid. It is also like temperature when you are accounting heat of a body, like heat energy and correlated parameter temperature, like that. So that these are associated terms. Well, you remember why I have written the associated terms means simply so for better understanding, for easy understanding, and you can compare what is the term potential? This is not first time you are getting the term potential. So even another potential also we referred earlier in the first year course, what is called gravitational potential, and we have defined it and even the formula written. And negative sign shows the gravitational potential is due to gravitational force, and the gravitational force is always attractive, can never be repulsive. Always attractive, can never be repulsive. Hence negative sign. If it is repulsive, you will get positive sign. So that you can see in case of electric potential, because electric potential due to electric charge, it has basically influence on other charges, electric force. So electric force can be attractive or repulsive, as you know. Like charges repel, unlike charges attract. Like charges repel, unlike charges attract. So accordingly, the electric potential can be positive, can be negative. However, gravitational potential is always negative, remember? Yes. Well, now with the definition, so this is a definition, mathematical definition. Remember, students, mathematical definition always helps to write a mathematical formula. Always helps to write a mathematical formula. However, what is the meaning of the term potential? Meaning means strength, you can say, level, you can say, how much strength of this charge at this point, how much is its strength at this point, like that. Level of water in a vessel, high level, low level. As you know, also I can give another example, the more related example. Why we are defining potential? Because in our later part, in the subsequent chapters, we are going to discuss the motion of charges. In this chapter and the previous chapter, we are discussing only static charges, that is charges which are at rest. In the upcoming chapters, we are going to discuss the movement of charges, and you remember always, charges will move always from one potential to another potential. Charges move only if there is a difference in potential. This is what we need. Hence, it is important. Suppose here more potential, there is another point less potential. So charges, positive charges move from high potential to low potential. Negative charges move from low potential to high potential. These are all the ideas we are going to establish in the subsequent discussion. We can also define one more term, potential difference. Potential difference we can define. Potential difference between two finite points. Potential between one finite point and one infinite point. This is infinite distance. Infinite distance is not definitely known. It is very, very long distance. The term infinity, very, very large. Not certainly known. So from that point to a point where it is certainly known, that is potential. If there are 2 points between which if you move the charge, if the 2 points are definite points, finite points, then whatever the work done to move between those two points, we say that is potential difference, electric potential difference we say. I write electric potential difference, electric potential difference. Say for example, P is 1 point. If I choose one more point, somewhere here, right, say P and R, and if you want to move charge from P to R, at P it has some potential and at R it has some potential. The difference is called potential difference. It is work done, same work done in moving unit positive charge from P to R. Like we can say, instead of infinity, now we should write P to R is equal to work done in moving from P to R divided by charge. Of course, we have referred Q as +1 coulomb, remember, unit positive charge. This is same definition, except that here 2 points between which charge is moved are the finite points, whereas only potential, the term to be referred from infinity. However, at infinity, potential of a charge is 0. Remember, at infinity, potential of charge is 0, because you know that as we move from the charge in any direction, distance increases, so potential decreases. And you will see how potential vary with the distance. And then you will see that in the when we derive the formula. Yes. So I write now SI unit of potential joule per coulomb, remember, and 1 joule per 1 coulomb is defined as 1 volt, VOLT, symbolically V. Potential at a point is said to be 1 volt. Potential at a point is said to be 1 volt. Define 1 volt. Define 1 volt. Potential at a point is said to be 1 volt if 1 joule of work is done. If 1 joule of work is done, what for? To move a unit positive charge from infinity to given point. From infinity to given point, that is 1 volt. Yes. This is the definition of SI unit of volt. If you want to write the dimensional formula also, you can write dimensional formula of V is, it will be written like this. So work done by charge basically, therefore it would be 1 in mass, 2 in length, minus 2 in time. This is for work done, and charge 1 in ampere and 1 in time. This on further simplification, 1 in mass, right, 2 in length, this is minus 3 in time, minus 1 in ampere. This is how it happens. This is the dimensional formula for potential. Friends, students, you can also note down all these points. I think if it is visible clearly, you can notice all these points. So next, what we are going to consider is, we are going to derive a formula for potential due to charge. We are going to derive a formula for potential due to charge. Like you remember, students, we defined and derived the field intensity due to a charge. If you remember, what is field intensity due to a charge? 1 by 4 pi E naught into Q by distance square. Do you remember? Field intensity due to a charge, 1 by 4 pi E naught into charge by square of the distance from the charge. Field intensity defined at a point. Is it not? Similarly, now we are going to define, of course, defined. Now we are going to derive the potential due to charge where at a point in an electric field. Potential due to a charge at a point in an electric field. It is a very simple method, simple way to derive the formula. And you will see how potential varies with the distance and as well with the charge. And you also remember, electric potential, unlike electric field intensity, electric potential is a scalar quantity. It has no direction, it has scalar quantity. Hence, electric potential, remember, can be positive due to positive charge, can be negative due to negative charge. And electric potential at a point can be 0 also. Like for example, potential due to this charge at infinity, how much it is? 0. And you will see mathematically also how at infinity it is 0. You will also see mathematically. Anyhow, potential due to charge, due to a charge or number of charges, either can be positive or negative or can be 0. So potential due to positive charge, positive potential. Potential due to negative charge, negative potential. And also by convention, potential due to positive charge is taken as higher potential. Potential due to negative charge is taken as lower potential. Remember always. Higher potential, positive potential. Lower potential, negative potential. Remember. So now students, after completing all the basic ideas of electric potential, remember, I repeat once, electric potential like gravitational potential defined in the first year gravitation chapter. And even I wrote the formula where capital G gravitational constant, m is mass of the earth, or you can take any mass for that matter, and r is the distance from the center of earth. If it is on the surface of earth, then you replace small r with capital R, where what is capital R? Radius of earth. So definition of electric potential difference follows on the same lines, except that it is between two known points, mathematically written, and SI unit written, definition written. SI unit is volt, you remember from now onwards, volt. Although commonly you remember we say voltage, high voltage, low voltage, the same term here defined volt. Then dimensional formula is also written, remember how it is written, all that you can notice. You should also remember positive charge, due to positive charge, positive potential, due to negative charge, negative potential. Yes. Now we are going to write an expression with the necessary mathematical steps. Well students, after defining some basic ideas of electric potential, now here is the arrangement made to get an expression. Look at the title, expression for electric potential I wrote. V is the symbol for electric potential. We are going to derive the formula for potential due to a charge in an electric field, is it not? And we follow the definition defined earlier, understand? And this will be important even from examination point of view. There can be a 5 marks question asking you to derive an expression for potential due to a charge, understand? Well, so here are the steps we follow, very simple steps we follow. Remember the arrangement what I have drawn. Plus Q is the charge placed in air or vacuum or the free space. If from infinity we are going to move a charge up to P, what is our aim? Our aim is to get potential at P due to this charge, understand? For that I have made an arrangement A and B, the 2 points separated by distance dx. Distance of separation is a small distance of separation. Now what we are going to do is, how much work would be done? How much work would be done in moving a unit positive charge from A to B over a infinitely small distance? And as you know, the similar methods we already employed. So what is that? How much work to be done in moving charge over a small distance dx between A and B? Then what we do? We extend this to no work done in moving from infinity to P. And you know how it is done? By the method of integration. Same steps we follow. So first what we do means how much is the work done in moving a charge from A to B. What is A to B? The 2 points which are very, very close, a small distance. Therefore obviously you have to do small work. And for that, I have written point A at distance x from Q, where electric field intensity is E. Direction shown, and between A and B, electric intensity will remain same. Electric intensity will remain same. Electric intensity will remain same between A and B. Why? Because intensity between 2 points A and B is same. Why? Because the 2 points are very, very close. That is why field intensity remains same. Well, now we can note that the electric intensity this is a formula of electric intensity. Call this as equation 1. And we assume that the E remains same between A and B. Remains same between A and B. Yes. Now, the small work done in moving the charge +1 coulomb between A and B of infinitely small distance yes, we are going to write, we apply the definition of work done. You know, work done is equal to force into displacement. Work done is equal to force into displacement. Here we write, we continue the discussion. Yes. That is, dW is equal to F into dx into cos theta. Definition. Work done, force into displacement, and theta, cosine of the angle between force and displacement. You remember, charge is going in this direction, force is in opposite direction. Further, we also write F can be written as E into Q into dx into cos of 180 degree. Because remember, field intensity opposite to the direction of motion of Q. This is Q. And Q value is 1. dW is equal to E into 1 into dx into, and you know, cos 180 degree minus 1. So what we did, students, between A and B, to move between A and B, what is work done we calculated. Now we are going to extend this for entire work done to move from A to given point. What is our given point? P is the given point. Well, now you can substitute for E as from equation 1, electric intensity, because between A and B, electric field is same. From 1, we can write dW is equal to, look at for E, 1 by 4 pi E naught, Q divided by x square into dx, of course with a minus sign. Look at minus sign. Look at the minus sign. Following, observe the steps carefully. Look at the diagram drawn. Look at the diagram drawn. Q is the positive charge located in space. Let P be a distance. P be a point at a distance R. P be a point at distance R, where we have to find electric potential due to this charge. Where we want to know how much is the work to be done to move a charge up to here. And for that we have chosen 2 points A and B. Remember. Now look at the formula dW minus 1 by 4 pi naught q by x square dx. This is small work done in moving the charge plus 1 coulomb between A and B of infinitely small distance. Infinitely small distance. Now what should be done? In order to know total work done, to move from infinity to given point, what should be done? We have to integrate this, and that too between the limits. What are the limits? What is initial point? Infinite. And when it comes to P, what is the final distance? R. And then you have to integrate the above equation between infinity and R. Yes. To calculate the total work done in moving from infinity to P, yes, integration dW is equal to integration between infinity to point R. What are the terms? 1 by 4 pi E naught into Q divided by x square into dx. And you know what is integration of dW? W only. And this is constant, minus 1 by 4 pi E naught is constant, even Q is constant. You are left with 1 by x square into dx. Now what is integration of 1 by x square? X square is taken to the numerator, x to the power minus 2. You can apply the formula x to the power n plus 1 by n plus 1 formula. You will get x to the power minus 2 plus 1 divided by minus 2 plus 1. Understand? Now, if you integrate this part, you will get minus 1 by x, and minus and minus cancel. Minus and minus cancel. I think better you have to copy this, note down these points very importantly, so that final simplification we can write. Final simplification. Observe carefully once again. Plus Q charge is given. Our aim is to find potential at P, distance R from Q. For that, we have made an arrangement. Remember, we have made an arrangement where charge is to be moved from A to B. First, we would like to know how much small work to be done to move from A to B. Then we will extend the same from infinity to given point. From infinity to given point. Look at the steps. This is electric field intensity at A, which is same between A and B. E remains same between A and B. A small work done in moving the charge plus 1 coulomb between A and B of infinitely small distance. Infinitely small distance. So work done, small work done is equal to force and displacement into cos theta, E into Q dx into cos 180 degree, E into 1 dx into minus 1, cos 180 degrees minus 1. And for E, substitute from 1 E substituted, minus sign is carried, and to calculate the total work done in moving from infinity to P, this is how the integration. Infinity is a distance, and for at P, distance is R. Now shall we proceed further? Shall we proceed further? The integration of this would be minus 1 by x. So minus and minus becomes plus. And we are going to apply the limits. In place of x, r minus 1 by infinity. So, and you know that 1 by infinity is a 0. You know that 1 by infinity is a 0. Then you will be left with 1 by r. So, and this is being a 0, it vanishes. And w, what is w? By the definition, v is equal to w by q, and w by q is 1, which means v is equal to w. Therefore, w plus l v, you will get this result. So finally what we are going to get? V is equal to 1 by 4 pi E naught Q by R. This would be the formula for electric potential due to charge. 1 by 4 pi E naught Q by R. This is the formula for potential due to charge at a point distance r from the charge. Look, you compare this with the field intensity, it would be 1 by 4 pi E naught, as you know, Q divided by R square. Now this is Q divided by R, otherwise it is Q divided by R square for electric intensity. This is Q by R for electric potential. Q divided by R square for intensity and Q divided by R for potential. And of course, potential also depends on medium. Similar to field, similar to force, field, force, potential also depends on surrounding medium. This is the formula with respect to air or vacuum. However, the same can be modified if it is other than air or vacuum. For other than air or vacuum, as we know, we write 1 by 4 pi E. And you will see that potential varies inversely with the distance. Inversely with distance, directly with charge, inversely with distance. Unlike field intensity, inversely with square of the distance. It is just inversely with distance. So well, in today's class, we have learnt very importantly the definition of potential, that is electric potential due to charge, and its formula due to charge. And this is one important question, can be given for 5 marks. And we also noticed what is the SI unit of potential, dimensional formula of potential, maybe they are for 1 mark questions. Maybe you will be asked to define 1 volt. Maybe you may be asked to define, you may be asked to write dimensional formula. The term 1 volt or in general voltage, the same term will also be used very commonly in the next chapter, that is current electricity, when we discuss. Of course, 1 volt is also defined with other formulas also. With respect to this also 1 volt can be defined. Well students, we conclude today's session, and in the next session we will continue to discuss more about electric potential. Like we are going to calculate the formula for potential difference. We are going to write the potential due to number of charges. It would be algebraic sum actually, because potential is being a scalar quantity. Potential due to number of charges at a point would be the algebraic sum of charges. Means if a positive charge, right, you will get positive potential. If it is a negative charge, you will get a negative potential. Students, remember the steps to be followed in order to arrive at the expression for potential due to a charge. Remember, due to a charge, a single isolated charge, which is taken as capital Q.